So now we're going to look at the properties of ionic compounds, which is based around how the lattice forms. So the lattice is the repeating structure, and for sodium chloride, the coordination for every sodium is 6. It's bound to 6 other chlorines. And same for chlorine, it's bound to 6 other sodium. So that's important, how many iron-iron bonds are there. That has an effect on how strong the lattice is and its physical and chemical properties. And so what we're going to look at is how much energy it takes to break that lattice apart. And so we get the solid there breaking into the gaseous ions is technically the term for lattice enthalpy. So we're looking at lattice dissociation enthalpy. Some other sources might be talking about lattice formation energy, which will be the same thing but a reverse sign. So just be aware of that if you're looking at the actual values of how strong the ionic compound is. And so what affects it, it's very similar to the metals. So if you have a very small ion that's very positively charged, it'll be, and same with this, a very negative charge, it's very small, the attraction will be much, much stronger than if it's quite large and not very positive or negative. Then it's a huge distance and a smaller force as well. And so that is similar to metals and alloys in strength. So the size of the pos neg and the distance, which is the size of the ionic radii. Okay, so looking at that, we can have a little bit of an analysis of the actual values here. So you can see that this one is getting stronger and stronger and stronger across. And if you look here, you've got these ones here is that's a little bit of a drop actually. I don't know why they inverted that. So that should be at the bottom because it's bromine and that's larger. And so these are getting smaller and smaller, these atomic radii. So that should be reversed. And then that would be in order. And then the oxygen is sort of a similar size, but it's a double charge, which is quite significant because these two ionic radii are pretty much the same charge. And so that's almost it's more than a double of the strength of the lattice. And so if we look at the cations, for the cations, the sodium is small but only 1 plus, and these are all double plus. So we're looking at the double plus here. And again, these two sizes will be very similar. Actually, the magnesium is actually going to be a smaller ionic size than the sodium. And so not only is it a smaller size, it's double charge. And so you can see that one is the best one we've got. Okay, so a little bit complicated. You need to apply your knowledge of ionic trends down and across periods to make sure you understand which number will be higher or lower in that. Okay, so moving on there, this one's just a specific example. I don't think these are too accurate, but I think for educational purposes, the only difference between this one is a larger, they're both plus, and this is the same anion. So this one obviously will have a weaker lattice enthalpy and come apart easier into a gaseous form. Now, the other points of this is as long as it's molten or dissolved, then the cations and anions are free to move, and in that case, they will conduct electricity. They do not conduct heat too well, not as well as metals anyway, because they don't have free electrons to move. So they are very strong because they have this pos-neg attraction, so they have high melting boiling points. Similar is volatility, so tendency to vaporize, it's almost the same term. And brittle because uniquely and interestingly, all you have to do is tap the thing, and instead of everything being attracted to each other, all of a sudden everything is opposed to each other, and so you tap it and the whole thing just breaks in half. And that's why, because they're all suddenly matched up to repel. Okay, so make sure you know those properties for ionic bonding. Very different to metallic, even though it is similar in charges and sizes of ions affecting the strength of the bonds. Moving on finally to solubility, you can stop there just to keep it simple. So it is ion dipole bonds here between the water and the anions and cations in competition with the ion-ion bonds of the lattice. And so if it's more favourable to be on this side, well, then it forms on this side, and it is for sodium chloride, but not for all salts. And so they're generally soluble, but not always the case. Okay, so I'll just go into a deep dive. Sorry to do this to you, but a lot of the salts are not soluble. Sodium chloride, highly soluble. It's like almost like it's 300 grams in 1,000 grams of water or whatever, whereas this is just down to like, less than 0.1 of a gram in the same volume. And so what is the difference between the two? So it's when you look at things like this, it's not just a simple idea of the lattice enthalpy, how strong the lattice enthalpy is. This one here is a huge lattice enthalpy compared to sodium chloride, but then that's the breaking of bonds. You also have to see whether the formation of bonds is going to be better off. And when water forms bonds with those ions, it's about the same value. So as far as enthalpy is concerned, they're sort of equal on both sides. But because this is going from 1 to 2 particles in a change of state almost to a liquid, because it's dissolved, there's a favorable entropy, so randomness. So that drives that reaction because everything else is equal to be favored, and so it is highly soluble. But with calcium carbonate, the lattice enthalpy is strong, but so is the formation of a lot of new bonds with the water. But there's a big difference still, this 800. Now, the entropy is also quite large, much larger than, 4 times larger than the sodium chloride, but it's still, relatively speaking, not large enough to have a significant effect. So, as you can see, there's a lot of factors involved in actually being able to predict whether something's soluble or not. It's not just, is it more random? Is heat favoured on one side or the other? It's quite complex. And so in this case, if you look at the numbers, it's just too strong, this lattice enthalpy, compared to the extra bonds that are formed with the water. So it just definitely favours the left-hand side, and it is highly insoluble. Okay, so I hope that's not going too complex. So if you're basically wondering why something's soluble, I think you should just say the lattice enthalpy is much, much stronger than the new bonds that will be formed with the water. Maybe just ignore entropy. Okay, lastly, solubility of salts. As you can see, there's a lot of weird things that go on here. I know for the glucose, it's going from ringed to straight chain, which massively increases its solubility, so it's exponential. So nothing's that simple, all right? You have to do a lot of deep dive research into any one particular chemical to work out why it's doing all these weird things in weird places. And so basically it's good to use experimental values because that is what's really happening, and the theory just helps you understand it, that's all. Prediction can be difficult with theory. So as temperature increases, solubility of salts increase. That's not going to be the case for volatile substances with gases. And so if this is the maximum amount of salt you can dissolve in, what is this one? 100 grams of water. So if it is less than that, then it's not saturated. You can still put more salt in it. If it's this, it'll come out as it won't dissolve unless you do a trick called supersaturating, which means you heat it up to a higher temperature and then let it cool slowly. But if you tap them, they'll suddenly realign and get to the right precipitation. So you can see that with the trick with water. You can cool it to 0 or -2 and it's still a liquid, but the minute you tap it, the whole thing instantly freezes. So I might put a video on that on the website if I remember. There are lots of other experimental videos that are worth watching on the website. And I'm going to leave this one. Can you come back to this one when you've done ratios for stoichiometry, which is because whenever you have ratios, you're best using cross multiplication. So if I just go through this, it's 40 degrees. At 40 degrees, 40 grams of the salt is added to 50 mils of water. Tell me if it'll dissolve or not. So you need to find 40 degrees and you need to find the salt, which is here. So that's 75. So I have a ratio, 75 in 100, and it's at 40. 50 grams, how much can 50 grams hold? And you put an X. So that's the ratio, cross-multiplying ratios will give the same number. So 100X gives that. And so for the 50 grams, you can get 37.5. All right, so really whenever you see anything that's got a ratio, try and use cross-multiplication of ratios. It makes life very, very simple. And so the question says we put 40 grams in and therefore it won't dissolve. There'll be 2.5 grams that won't dissolve in there unless we're using a supersaturation trick or some other factor we're unaware of.